Hello guys, welcome to my YouTube channel AZ Neotech. Today we are going to discuss a topic about heap data structure. So let's look at what is heap. A heap is a tree-based data structure which is nearly a complete binary tree. So what is a complete binary tree? A binary tree which has a root node without any child is also a complete binary tree. Also, if it has child nodes, it should be two child nodes present to make it as a complete binary tree. So in case of heap, it is a nearly complete binary tree. That means either root node should be present standalone or else it should have at least one child to make it as a nearly complete binary tree. So what is the difference between heap and tree? So in case of heap, which can be implemented using a node-like structure that has a value as well as pointed to other its child nodes, left and right child. So in case of heap, what we can do is like we can use an array data structure to implement the heap based upon some property and relationship between the parent and the child. So that we gonna discuss in the later slide. So how the heap is maintained? A heap is maintained using an property called heap property or invariant. So based upon this invariant, we have two types of heap. We call it as min or max heap based upon the invariant type. Also, it can be called as min or max priority queue, which we gonna implement later in this after this lecture. So what does the heap invariant do in order to maintain the min or max heap? So let's take a max heap invariant, which is nothing but I'm going to show you a max heap data structure. So heap tree-like structure. So as you see here, we have a root element with two childs. So if you closely look at each nodes, you can see that the root element is greater than both its child. So both of its child. So 100 is greater than 19 and 36. So as you see here, 100 is our parent, 19 and 36 are our child. So for any child node C, if P is its parent, then value of P should be greater than or equal to child node. So this is the heap invariant property of a max heap. In case of min heap, which is the reverse. So the parent node should be the lesser of both the childs. So that's how we maintain a heap. So as I said earlier, this tree-like structure we can be maintained in an array. So when you look at the array, you see the parent is at P index 0 and the childs are at index 2 times the parent plus 1. So for this index 0, the child is at 1 and the next child is at 2 times the parent plus 2. So 2. So when you take the child of 19, which is 3, the 17, and 4, 3. So both are less than the value at index 1. So that's how we are maintaining a max heap property. So how do we build this heap? So this heap can be built using a method called syncing or ShiftDown or BubbleDown. So let's take a closer look at what it is. So imagine we have a heap like this. We have a data structure like this. It's not a heap because it is not satisfying the heap invariant property because its root node is not greater than both of its child because it is less than the right child. So in order to maintain the heap variant property, what we have to do is like, so we have this array of length 3 and 3 is our parent. So from the parent, we will check whether we have a left child which is less than or equal to the length of the array minus 1. So its left child is this one, so its index is 1 as you see here, and it should be less than or equal to the length of the array minus 1. So 3 minus 1 is 2, so it is less than or equal to 2. So that satisfies it, and then we need to fix the left and right child. So we fix the left and right child. Yeah, as I said earlier, this is our left child 2 and the rest is our right child 9. So what we need to do is like we need to find the greater among the two childs, left and right. So we fix that greater child. So here 9 is the greater. Next we will exchange the greater child with the we will exchange the greater child with the parent if it is greater than parent. So 9 is obviously greater than the parent 3, so we need to exchange it. Yep. So now the greater child becomes the parent. As you see here, we exchange 3 and 9, and now 9 becomes a parent. And when we check again, this 9 satisfies the heap invariant property. That's how we are building this. This method is called shrinking. So we synced from 3 to the bottom in order to find its correct place. So we call this as syncing. So as you see here, we start from this looping condition. So the left side should be greater than or equal to, less than or equal to the length of the array minus 1. So we fix the left and right child, and we take the greater child as left child, and we check whether the left child is in order to find whether we have right child or not. This condition stands. So then what we need to do is, like, we check left and right child who is greater. If right child is greater than left child, we will fix right child as our greater child. Then we need to check whether our parent P and the greater child, parent P, is less than the greater child. If it is, what we need to do is, like, we will exchange the parent and the greater child, and now the greater child become the parent. So this is our formula for deriving the heap invariant property. So let's go to the process, heapifying process. So initially we have an array, so which is of increasing order from 0 to 9. So the 0th index will be 0 and the 9th index will be 9. So the total length of the array is 10. So we are going to apply this sync property. So for applying the sync property, what we need to do is, like, we will go from the middle of the input array. So we will come from 5. Okay, and then we will sync 5. So once we started to sync 5, so the max heap in the first pass, there is no change because this is at index 5. So when you multiply this parent index with 2, which is 10, plus 1, 11. So there is no 11th index which is less than or equal to the length of the array minus 1. So it won't go into this loop. So the first pass we don't get any change in the heap. So in the second pass, what we need to do is, like, we will decrease from the mid index minus 1. So we will fix our index as 4. Now we find some heap property is not satisfied. So 4 and 9 is not satisfied. So we will exchange it based upon this syncing condition. And then once again we go down the array. So now our current index is 3. We sync 3. So now we found out that the element at 3rd index and 8th index is not a heap satisfying the heap invariant property because its left and left the left child of this element is this one according to this property. So we will exchange it, and in the next pass we will exchange 6 and 2, and in the next pass at current index 1 we find the property that is not satisfying the heap invariant and exchange it. And now once again we run this condition because it is a while loop, and we found out that another property at 1 which is also not satisfying the heap condition. So we will exchange it 4 and 1. And then the last pass we do the same thing. We will exchange 9 and 0, 0 and 9 from 9 and 0, and then we exchange 0 and 8, and we exchange 0 and 7. So this is our heapified array. So let's go on to the implementation with Java, and also I will give you a bonus to do how to do heap sort. Welcome to the coding implementation of my maximum priority queue with the help of heap data structure. So with this coding implementation, I'm going to add a bonus how to do heap sorting, which is a scalable algorithm to sort n elements with a worst case time complexity of n times the log n. I will paste some of the solution that I am going to use. One is swapping 2 elements, other one is finding the less than of 2 elements, and also to show the arrays that are heapified using the show functionality in the MaxPQ class. So let's start with the implementation of underlying data store. So I am going to use the array, so we call it as integer array of priority queue. So this array has a property to hold its size, we call it as n. So I will implement a method called size, so which returns the integer value, so the size of the element in the array. So we will return n. So in order to head start, we will add a constructor of MaxPQ, which accepts integer input array, which is not heapified. So what we need to do is like we need to heapify this array. So that's what I given here in the input. Our input is range from 0 to 9, which will be applied to our MaxPQ constructor, which will heapify the input array. So we are going to the heapify phase. Okay, so in order for a heap to work, we just need to iterate from the middle of the element in the array. So we do n by 2, so it should be greater than or equal to 0, and we will go from the back, from the middle. So first we will fix the size of the input array. Input array dot length, so we will fix n as length. Okay, and we will go on to the heapify phase. So during the heapify phase, what we need to do is like we need to sync the parent. Here the parent, here in our case the parent is the mid element, which is k. While doing the heapify phase, we sync from the parent element. So we will create a method called sync. Okay, we call this as parent. So our looping condition is while we need to check the left child of the parent, so which is nothing but 2 star p plus 1 should be less than or equal to our input array minus input array length minus 1. So in order to check whether the left child is inside the array limit, which is not out of bounds of the limit. So once we done that, we will fix our left child, which is nothing but our 2 star p plus 1, and with the help of the left child we will put on our right child as well, which is nothing but 2 star p plus 2 or left child plus 1, whatever it is. It's up to us to implement it. So we need to fix the greater child, greater among the two. First we will fix the greater child as left child, and we need to find whether we have right child or not. So in order to do that, we check the left child's index value is less than n minus 1. So if it is less than n minus 1, we have right child as n minus 1 position. So we can use this condition to find the greatest among the left and right child. Okay, after that we will fix our greatest child as, once the left child is less than right child, we will fit the greater child as a right child. So now the right child becomes our greater child. What we need to do is we need to check whether the parent is less than, parent index is less than the greater child index. So sorry, it should not be less than. So yeah, and once it is less than, if it is not less than greater child, we will break it. Otherwise we will exchange the parent index with the greater child index. Okay, then now the greater child become the parent. So that's it. So we have our heapify process and just run through our code. So this is our array. So in order to print out our array, what we can do is like array start to string. So our input array is like this. I will put a breakpoint. So see here, our input array is this one, and once it goes out of, oops, we have an exception. So what we have done wrong, I didn't initialize this array. So we will initialize the input array with this priority queue. Then we start the debugger again. Okay, fine. Okay, let's check our output case. So the index at 0, 9, which is greater than 8 and 6, 8 is greater than 7 and 4, 6 is greater than 5 and 2, and 7 which is greater than 0 and 3, and 4 which is greater than 1. So our heap invariant is restored and we have heapified the array. So let's go on to the bonus sorting. So we need to sort this array, sort this priority queue based on increasing order, and I will show the result after sorting. Sorted priority queue. Okay, so basically we need to implement this one. Okay, it's gonna be with method. So we are going to sort the heapified array. So we start whether n is greater than or equal to greater than 0. Okay, if it is greater than 0, exchange our first element with n, last element, and then we will sync our first element. Then what we need to do is we need to restore the priority queue length. So let's run it. After sorting, we have the sorted array 0, 1, 2, 3, 4, 5, 6, and 8. Basically nothing but we need to exchange the topmost element with the last element in the array, which is at the index 9. We will exchange it and we will sync it to the bottom. So our topmost element is a maximum value that will be going to the last index, and then the heap invariant property is broken, so we need to restore it by using sync method. From sync 0 up to n minus 1, which is 9. From 0th index to 9th index, we will apply the sync method. Thereby our array becomes sorted, and since we have reduced the size of the array, we need to restore it by the length of the array. So thereby when we try to sort and show the array, so the priority queue, we will get the sorted priority queue. That's all for the implementation of maximum priority queue and bonus sorting function. Hope this video finds useful. In the next video, I will explain about how we can insert, delete, and find the maximum element in the max priority queue. So as a bonus exercise, you guys can try to implement the minimum priority queue. That's it from you, signing off. Thanks for watching. Please subscribe to the channel.